So I'm talking about linear programming, so time is short. I just quickly give you an introduction. Oops. Yeah, so I'm going to talk about the linear programming and the algorithms and the advanced in simplex method, the two popular methods, and another interior point method. Then I talk about the first order, so the new methodologies we try to develop. Then I'm going to talk about summary ongoing research. Okay. So first, linear programming. Linear programming, I don't know how many people know this. This is a computative decision models, which in 1972 won the Nobel Prize by this couple of gentlemen. So this is several giants in this field. So Kontorovich and on the right, and George Danzig, which is the simplex method, and also Koopman. So right now, it was invented in the 1940s. So at the time, people can use a pen and a pencil to solve a decision problem with maybe 10 decision variables. Now the software is so matured, we can solve millions decision variables, millions constraints in a couple of minutes. The question is, can we push them for solve billion variables or even trillion variables? So that's the research going on. The mathematical formutation is just, X is your decision variables. You try to maximize a linear function or minimize a linear function, which is C. We call the objective vectors. You have a matrix A, so Ax less equal to B or equal to B, whatever. X could be non-active. So this is a algebraic form of linear programming problems. Okay, this is sometimes we call this is. Oh my God! I have a pause. Okay, so geometrically, what's going on? Geometrically says all the decision variables are constrained in some kind of a polygon. Okay,
how's that?
So, yeah, this is better actually. Yeah, so. The question is, all the points in the green and in the red area are your feasible points. So you want to push some objective contour to some kind of a vortex. So that's where your optimal solution is about. So in two-dimensional space, that's easy to see, but you can think about this is in the millions and decisions. So it's not easy to see how to find those decision variables. Okay. So what's the simplex method? As I said, George Danzig simplex start from some vortex, move along the edges, and gradually reach the optimal vortex at the top. So that's one popular method. Another method is called the interior point method, which is go from the interior of the feasible polygon and try to generate a good direction and reach the optimal vortex extreme points from the interior. Okay, so far, this is two power horses to solve linear programming. So linear programming software, like Simplex, Groovy, and all these kind of things based on these two methods. Okay, so it's a multi-billion-dollar business, and people can sell linear programming software for living. Okay, and many people use. Okay. I'm just giving you a quick advances on the simplex method, which is the method which we talk about. George Danzig invented, but somehow in the past nobody knows. Can you give a guarantee how many steps you can reach the optimal vortex? So this is called the complexity analysis. It's like a machine-independent computers, like efficiency analysis. Basically, we say how many arithmetical operations I need to solve for the optimal solutions. Okay. For quite some time, we don't know how efficient the simplex method it is. But we also know for MDP, I don't know how many people know the Markov Decision Process. So I'm going to quick. And these kind of solve very useful problems. But this problem, MDP, is a special case for linear programming problems. So people use it. Okay. So we don't know how efficient, although people use it in practice. For quite some time, we don't know, can we prove that method is efficient or not? So I just give you one sense. A couple of years ago, and actually in 2010, we proved simplex it's not only polynomial, but strongly polynomial solve Markov decision problems. So that was a breakthrough. Okay, and you also can prove, and another popular method is called a policy iteration method for people in machine learning, and MDP, policy iteration method, very popular method. And we also proved, and the MDP, power policies, which actually invented by John Howard from this university, and who also proved these strongly polynomial time algorithms. Okay, then there was there also at the same time there was also many advances on the interior point methods. Okay, interior point method gave, for example, I'm going to go very quickly. This is the problems and how to take traditionally the matrix have 2 dimensions, m rows and columns. Usually, complexity depends on the large of the 2 dimensions. But this gentleman's proof that complexity only on the smaller the dimension of the problem. So that is some kind of improvement. Okay. So this is the code. Also, they proved you can solve maximum flow very, very efficiently. So this is a couple of people. And also one of the authors called Aaron Sitford, which is on the bottom, and actually is going to join Stanford MSE very soon. I hope you can get him in the ICME as well. Yeah. So yeah, there was another efficient method, same thing, Sitford. Also have some progresses and improve the performance of the interior point method. So the 2 powerhouses and which really have a lot of progress recently. But the question is, those 2 methods somehow still need to involve a matrix. Okay. Now in today's research, if you want to solve a problem with billion by billions, involves a billion by billion matrix, it's not that easy. Okay, done. So people are looking for the so-called first order method. What's the first order method? It's the method that only take matrix multiplied by a vector. But you don't need to inverse it. Okay, you don't need to do that procedures. So that's hope. Besides, the first order method usually are very easily parallelable and put into distributed platforms like GPU or some other cloud or stuff. So I just wanted to say, and early work have some von Neumann has already done, and in these directions. Okay. There was some kind of first order method taken like, but complexity is very, very complicated. Okay, but however, we also made some progress on this. It's called the first order potential reduction algorithms. So we only need n to the power 1.5, and then gamma, which is the Lipschitz condition number, then take 1 over epsilon. Epsilon is your target accuracy for the solutions. So this kind of algorithm, recently we also be able to remove this gamma. So it's become really a persuasion scheme. So we tried now and try to implement it and to see, I think very likely, maybe in a couple of years, we should be able to solve a mini problem with billions of variables and stuff. Especially when the question is sparse. I'm also, another direction how to solve a big size problems is called alternating direction method of multipliers. So basically say, I have a billion variables. Can I break them into 1,000 blocks? Each block only have a million variables. Because I can solve decision problem with million variables very fast. Can we solve them alternatively? Okay, first solve 1 block, keep other fixed. Solve second block, keep other fixed. So this is called augmented Lagrangian. So your objective is broken into block, you constraints, but you have each block, you have a p blocks, okay? So what you do is, you create these augmented Lagrangian functions, which is relax that constraint into objective functions. So what you do is, you solve this problem block by block, okay? So each block, you keep other fixed. When that block is updated, you replace them, update it, then solve for second block. Okay, So you just alternate and then update them by launching multipliers. Okay. So this kind of a scheme is very popular. Okay, and which very nice theoretical result is proving if you only have 2 blocks. For example, if you have a billion variables, you break them into 2 blocks, and it works beautifully. You can prove convergence, reach the target. But however, well, break that 1 billion variable into 2 blocks doesn't help me much. I want to be able to break into more, 1,000 blocks, 1 million blocks. So I need size for a small problem. So for quite some time, people don't know how this algorithm works if a block is more than 2 number of blocks. Okay. Well, people guess it should work. Okay. Many people implement. Most time works. But unfortunately, we prove, and we did find a counterexamples. When you have 3 blocks, the algorithm fails. Miserable, actually. Okay. Actually, the problem just solve a system linear equations. So the slow objective functions just solve system linear equations in the divergence. And also, you can actually prove, or you may say, oh, because you have a lousy starting point, so if divergence, maybe starting a better point for convergence. But we actually prove, if you randomly generate the initial points, the divergence will prove to 1. So it's generic. It's not the good bad luck. Okay. So you can draw the pictures. The solution should be go to zeros, but actually the magnitude of the solution go to infinity. Okay. However, we do find a good cue to solve this, overcome this difficulty. Remember my update first, update second, update third. I always follow that same order. What about I randomize the order in each run? Everybody understand what I'm saying? Yeah. So among those people, I randomly select one update first, but the remaining, I randomly select is called the sample without a replacement. Okay? Now it'll work. Well, numerically it works. Okay, so this is what I said. You randomly permute, okay? Actually, always converges. But the same bad problems. But that problem always diverges. This problem